Alright, we're going to go ahead and get started with Lecture 5. The topic that we're going to be addressing on Lecture 5 is the all-important topic of entropy. Entropy is an area where sometimes is difficult for students to understand, but it is a topic that you must understand in order to fully understand thermodynamics. Entropy is going to be the governing force or idea of why processes happen or if they do not happen. So let's go ahead and look at the essential questions. For this lecture 5, these are the questions that you need to make sure that you are able to address for the quiz that's coming up after this lecture, as well as you really just need to know these questions for the exam. So this is what you should be able to answer. What must occur for a chemical reaction to be spontaneous? What are the indications if an entropy change of a system is increasing the disorder of the surroundings? Right? So you should be able to address these two questions when we're done here. Okay, so let's look at question number 1 in your lecture handout under Chapter 5, Entropy. Question 1 says, what is a spontaneous process? What do we mean by that, a spontaneous process? Well, if we were to write down a simple type of definition, you would simply say a spontaneous process occurs when changes that occur naturally without the need to do work. And so I guess you could say the most important part of this is that a spontaneous process naturally occurs without the need to do work. So without the need to do work. Those are the key points there. Alright, let's look at question number 2. Question number 2 states, what is a non-spontaneous process? Well, essentially a non-spontaneous process is going to be just the opposite of a spontaneous process. In order for a non-spontaneous process to occur, you're going to have to do some work, or work is going to be done. So we could simply say changes that occur only if work is done. So if work is done, then it can drive a non-spontaneous process. The other thing to look at is that processes let me erase that. Let me start all over there. Okay, processes that are spontaneous in one direction are non-spontaneous in the opposite So again, if you think about a spontaneous process, it's going to occur naturally and you don't need to put any work into it. Whereas a non-spontaneous process requires work in order for it to occur. And so if you have a process that proceeds in one direction is spontaneous, then the opposite direction it will have to be non-spontaneous. Okay, let me erase this. Let's go to question number 3. Now, question number 3, we're going to address a lot more in the preceding questions, or the questions that come after. So the question states, what must occur for a chemical reaction to be spontaneous? So what do we have to consider here? So first of all, there are two major reasons why a reaction would be spontaneous. The first one you're familiar with already, and that is exothermic. So if a reaction is exothermic, it will drive a spontaneous reaction, or reaction will occur naturally. And this is because heat itself is being released into the surrounding environment. So now that's very important to make note of, is because heat is being transferred to the surrounding environment, is helping to increase the spontaneity of the process, or the chemical reaction. So energy is dispersed basically dispersed to the surrounding environment. Alright, the other thing that drives a reaction to be spontaneous is if the if the surrounding environment becomes more disordered. Alright, and we're going to address what this means, more disordered, in just a minute. But basically, those are the two big driving forces for a spontaneous process: exothermic and more disordered environment or surroundings. Alright, so let's look at question number 4. How does a spontaneous reaction relate to the rate or how fast a reaction goes? Well, what you have to understand is a spontaneous reaction can occur, but it tells us nothing about how fast the reaction will go. So it's simply a spontaneous reaction does not determine how fast a reaction will occur. Alright? Now this is a very important statement. You really need to make sure you have that in your notes and understand it very well. Because you can have a spontaneous reaction, but it could take forever for it to actually occur. It doesn't have to be fast just because it's spontaneous. Sometimes in our society we get the word spontaneous mixed up, and we think spontaneous means that it happens fast and right away. But that is just not so. It's not true at all. Spontaneous just tells us that the reaction will occur, it will take place without any work done to it, but it doesn't tell us how fast it's going to occur. It could be fast or it could be slow. Alright, so just make sure you understand that for question number 4. Alright, question number 5. This is where we're starting to talk about disordered systems or environments, and we'll get into our all-important topic of entropy here. All right. So what is entropy? What do we mean by entropy? Well, essentially, when matter and energy, when matter and energy tend to disperse, and become more disordered. All right, more disordered. So entropy really is referring to how disordered a system is. Okay, what do we mean by this exactly? Well, think about your bedroom. Your bedroom is put together in such a way in which your mother or father wants it to be in an ordered state. And when it's all messy, it's completely disordered and not the way your mother wants your room to be. And think about if you have your room arranged how you want it and it's all nice and ordered and structured, and then you start moving a few things around, it starts becoming more disordered. And the more things you begin to rearrange in your room, the more disordered your room becomes. Some of your rooms are probably extremely disordered. And so what we find is that nature tends to move towards a disordered state. In other words, nature likes randomness, disorder, chaos. And so the more disordered and chaos the universe becomes, the more you could say stable it is. And when a process creates a more disordered universe or a more disordered environment, the process is more spontaneous. And so spontaneous processes have everything to do with creating a disordered state. And so when we look at matter and energy, the reason why exothermic processes create a spontaneous process is because energy is being dispersed, and that dispersive energy creates more disorder in the universe. And the more disorganized or disruptive matter is, also the more disordered, the more spontaneous a process is. So the idea is that entropy measures how much disorder the universe is. Okay? Now when we're dealing with chemistry, we're going to deal with what is called the change in entropy. The change in entropy is symbolized by delta S. Okay? And this stands for change in entropy. Change in entropy. So we can have two things, okay? An ordered state have low entropy, and a disordered state have high entropy. Okay? So these two things are very important to understand. When you have a very ordered system, or sorry, a more ordered universe, or more ordered surrounding, then you have low entropy. But when you have a more disordered universe or surrounding environment, then the entropy is high. Alright? So let's again summarize this whole idea. Entropy measures the disorderness of the surrounding environment or universe. The more disordered the state is, the higher the entropy. The more ordered the state, the lower the entropy. Alright? Okay, so I'm going to erase this. Erase this for a minute. And then let's go and look at our next question and see if we can make more sense of this idea of entropy. Alright, the next question, question number 6, states, what is the second law of thermodynamics? The second law of thermodynamics relates to entropy. And basically, the second law of thermodynamics states this: the total entropy of the universe in any spontaneous I lost my slide. Alright, let's start again. I don't know why I lost my slide there. Alright, so again, the total entropy of the universe increases in any spontaneous process. Okay. Okay, let's actually, before we go on, let's kind of explain this a little bit. Okay, the total entropy of the universe increases in any spontaneous process. So, in other words, if the process is going to be spontaneous, then the amount of entropy in the universe must become higher, or the amount of entropy in the surrounding environment must become higher. And that simply equates to this: the more spontaneous the process, the more disordered that process is going to make the surrounding environment. Alright, so let's say that again. So if a process is going to be spontaneous, the amount of disorder or randomness in the surrounding environment will be increased. So think about a combustion reaction, one in which you're burning something. When you're burning something, you're going to create more disorder in the surrounding environment because you're releasing heat energy, which is creating more disorder, and you're going to create more gases, which is going to create more disorder. So burning something is a spontaneous process because it increases the disorder of the universe. And that is the key. Again, write this down. Understand this. If a reaction is spontaneous, then there is an increase in the entropy of the universe, or in the surrounding environment. So we can use the second law of thermodynamics to predict. Okay, so we can use this to predict whether a process will be spontaneous. Overall, this is probably one of the most important laws in all of science, right here. In fact, you might even want to write that down and make note of it. The second law of thermodynamics, or entropy, is probably the most important law, or one of the most important laws in all of sciences, because it is this process, the second law, that will tell us if a process will occur or not. So it's really important. Okay, so this is what we're going to do. We're going to go ahead and take a break here and in this video. And so we're going to call this part 1. And then what we'll do is we'll pick this up again in the second video and finish up entropy in part 2. Alright?